Welcome to the course on Machine Learning Interpretability. In this course, you will learn how to make sense of the outputs of your machine learning models. My name is Soledad Gali. I am a data scientist and I will be guiding you through this course. As a data scientist, I worked in finance and insurance companies where I created machine learning models to assess credit risk, insurance claims, and prevent fraud. Now, being able to explain why a model made a prediction is key within these industries. Investors may want to know if the variables that go into a risk model make sense and are thoroughly scrutinized. Regulators may want to know if the models are treating customers fairly and abiding by the law. Clients may want to know why they were rejected a loan or given a certain interest rate. And the people within the company, like fraud investigators, may also want to know what made the model make such a prediction so they understand what they should look for in a potentially fraudulent application. But understanding the outputs of the models is not only critical for tightly regulated companies like those in the finance and insurance sectors. Understanding models that make medical diagnosis, for example, is key to providing suitable care. And if you follow the news, you probably heard of the scandals that are being exposed more and more often because people use models in production that have not been scrutinized enough. So in this course, we will learn how to make sense of the predictions of our machine learning models. We will seek to understand what made the model make one prediction and not another. Now, there are certain machine learning models that are intrinsically explainable. We know how they work, and we know how they arrive at their conclusions, or how they produce their outputs, in other words. The two key examples of intrinsically explainable models are linear regression and decision trees. And we can also explain slightly more complex models like random forests and gradient boosting machines if we take a look at the architecture of all the trees that compose them and then make an aggregated interpretation. So we can easily explain intrinsically explainable models if we examine their components and parameters. There are other models that are inscrutable by design, the so-called black box models. The most obvious example is neural networks. We can still try and explain the predictions of these black box models by using what are called post-hoc or model-agnostic explainable algorithms, like permutation feature importance or partial dependency plots, among others. We can also explain or interpret machine learning models globally or locally. In global interpretation, we seek to understand what makes the model make certain predictions in general or on average given a certain dataset. The clearest example is to examine the global features importance one way or another, which is probably what you're most familiar with. We can also interpret models locally. Local interpretation consists in understanding for this particular customer, for this particular claim, or for this particular image, what made the model make this prediction. In this case, we want to know which features drove the model prediction for that particular example. Now, going back to intrinsically explainable models, we can interpret them both globally and locally by examining their components and parameters. And for black box models, we can use global methods like permutation feature importance, partial dependency plots, or local methods like LIME, SHAP, and the individual conditional expectation, among others. So what is this course about? In this course, we will take a deeper look at what interpretability is in the context of machine learning. We will understand the challenges to interpretability and learn how we can make our models more interpretable. With these key concepts out of the way, we will then move on to learn how to explain intrinsically explainable models like linear regression, decision trees, and random forests, among others, both globally and locally. And then we will move on to model agnostic methods or post-hoc explainability methods for global interpretation like permutation feature importance or partial dependency plots. And finally, we will learn about local explainability methods like LIME, SHAP, and the individual conditional expectations. We will explain what the methods are and what their advantages and limitations are. We will dwell deeper on the trade-offs and risks of using black box models followed by post-hoc interpretations, so you can be well placed to decide if you and your organization want to run those risks. And as always, there will be plenty of code showing how to implement each and every interpretability method in Python. All topics include hands-on Python code examples in Jupyter notebooks that you can use for reference, practice, and reuse in your own projects. We will explain machine learning model outputs using well-known Python libraries such as scikit-learn and stats models, and specific packages such as LIME and SHAP, among others. As a result, you will have materials covering both the theory and practice regarding machine learning interpretability. By the end of the course, you will know how to explain the predictions of your machine learning models both at the global and the local level, and you will be able to choose which method best suits your particular model, data, and circumstances. So check out the next video for a breakdown of the complete course curriculum. If you're looking for a particular method, algorithm, or topic, make sure to check the full curriculum at the bottom of this webpage, where you will find what exactly we will be discussing throughout the course. In the unlikely event that you don't find this course useful, there is a 30-day money-back warranty, so there is no reason to wait. Enroll today and let's start making sense of those models. See you in the course.